implicit differentiation when we have to find the derivative. Again, it's finding the derivative of the y with respect to x. And guys, most of these examples, in most of these examples, you'll be asked to find the derivative of y with respect to x. Guys, the key thing here, first thing to note is that this is an implicit function because x's and y's are basically together. And again, for this particular equation, we may still be able to explicitly solve this for y, but it is still going to be extra work. And then taking the derivative of everything, again, it's actually going to be a lot of work. So guys, we can avoid all that work if we just use this idea or this technique of implicit differentiation, which is just a different word for using the chain rule. And guys, the most important thing is whenever I see this y, we kind of think of that y as not just y by itself, and we already know y is a function of x. And how do you actually write it? What is the notation for that? You write it like y of x. Okay, so guys, keeping in mind this notation, what I'm going to do here is, and I'm going to do it only for this example because this is my first example that I'm trying to share with everyone here. Guys, once we understand how to actually follow and how to do all these steps, then from the next examples, I'm not all the time going to write y of x, but back in our minds, we have to always think of y as a y of x. Okay, so here I'm going to write this as x squared, and wherever I have y, I'm going to write this as y of x, and then this is minus y of x whole square, and that equals to 4. Okay. Now guys, in order to find the dy over dx, so that is because that is what we have to find. That's what it says, find dy over dx. So our goal is to find the derivative of y with respect to x. Again, we can clearly see that it is going to be a little complicated for us to just solve it first for y and then take the dy over dx. And that is what we have been doing so far with all the examples. With all the techniques, there was always a nice explicitly written out function in terms of y equals to something, and then based on what the function looks like, whether it's a rational function, a product function, or whatever trig functions or whatever, we have to use a combination of rules or different rules to find the derivative. But in this case, since it is not explicitly written in terms of y, one has to use something slightly different. So what one has to use here is, first of all, we have to apply the derivative on both sides, and that is something that we do all the time when we have to when we have to deal with or when we have to work with implicit functions. So step number one is we apply derivative on both sides. So applying derivative on both sides is something like if you have an equation and you add something to the left hand side. So if you add something to the left hand side, you have to add something to the right hand side. Again, if you have an equation and you apply or you take a log on left hand side, you have to take the log on the other side. Guys, the same idea extends to taking or applying derivative on both sides. That is going to be our step number one, take the derivative on both sides. So I'm in for this particular example, and most of the examples I like to write the steps clearly. I'm going to write the steps here. Take the derivative on both sides. So take derivative on both sides. So guys, keep in mind, we did not try to do anything with the original equation. We just let it be the way it is. And that is going to be very important, guys. If we try to isolate for y, for these types of equations, it's going to make our life a little bit difficult. It's going to make it more complex. So we don't want to do that. We straight away want to take or apply the derivative on both sides. So let us go ahead and do it. So d over dx. And guys, this is the section. If you have been watching my videos, I'm totally fine with using the notation y prime or dy over dx. But guys, this is the section where it is very important to go back and use the d over dx notation. And I'm going to use d over dx notation here almost all the time. So d over dx of then, because we are applying to the left hand side and the right hand side, so I'm first going to write this whole thing, and then we will break it down into two pieces. Obviously, because these are two quantities, so we have to break it into two. But first, I'm going to write the full step. I'm applying to the left hand side, and I'm also applying to the right hand side. So I have to do the d over dx of positive 4. Now, let us start simplifying things. Guys, again, we know that we can just simply distribute the derivative. So it is like d over dx of x squared and y of x. Keep in mind, this is a product here. And then we can close that parentheses. Then what do I have? I have minus d over dx of the second term. which is y of x, and whole square. And guys, what is the derivative of constant for? The derivative of constant, we know for that matter, is for any constant is 0. So that's just 0. And getting a 0 here is actually going to make our life easier, okay? Once we start simplifying. So guys, now let us start simplifying things here. Obviously, we can see this first expression is a product of two expressions, and we want to take the derivative with respect to x. So we have to use, one has to use the product rule. We can think of this as f times g, right? F times g, and let me remind you the product rule, guys. The product rule says f times g, derivative of the product is f prime times g plus g prime times f. Okay, so let us apply the product rule here. Using the product rule, first I have to find the derivative of x squared, which is just 2x. All I have to do with this is I just have to multiply by the g function, which is just y of x. Then guys, plus I have to find the derivative of the g function. Now y, I don't know the expression for y, but all I can do here is I can just simply say dy over dx. And then if I try to multiply by the derivative of the inner, but guys, what is the inner here? The inner is x, right? What is the derivative of x with respect to dx? It is just 1, so I don't have to even write it, okay? And then I have to multiply this guy by the f function, which is just simply x squared. That takes care of this first piece right here. And then guys, minus derivative of this function. So guys, to find the derivative of this function, one has to use the power rule, or you can also think of that as using the chain rule. So using the power rule, what do we do first? We bring the exponent in the front, and then whatever we have, like I kind of consider this as a big X. In this case, it's not just X, it's y of x. And then this whole thing has to be raised to the power 1, but I don't have to really write it, it is understood. But we cannot stop right here. Using the chain rule, we know that, and we have already talked about the chain rule. Guys, we have to multiply by the derivative of the inner, and the inner here is just this y of x, so we have to multiply by dy over dx. And that is the reason why I want you guys to think of y not just as y, but as a function of x, and kind of write it as y of x, because now from here we can see that we have to bring the 2 in the front, then we use the power rule on this, but we still have to multiply by the derivative of the inner. I mean, you can still put an x here, it's a function of x, okay? Guys, this is step number 1, step number 3 here, and this is still equal to 0. Now our goal is to find dy over dx, so we are carefully going to simplify things, and then we are going to see how we can isolate dy over dx. Guys, please do not let this equation, which is like a differential equation which has derivatives, confuse you. From here, guys, it's mostly like solving an equation, a simple equation, okay? So I'm going to go over all the steps, and you can see how we actually are going to solve this. It is very similar to solving an equation, okay, like a simple algebraic equation. So what I'm going to do here is, this is 2x, and guys, at this step, I want to get rid of these x's with as y as a function of x, so that it's not confusing for us. And then second piece, I'm going to write x squared in the front, and then there's of course dy over dx. Guys, we like to write the algebraic functions in the front, and then the derivatives, guys, minus 2y, and then I have dy over dx, and this equals to 0. Guys, all I did here was I got rid of this parentheses. I mean, I don't know why I put these parentheses. I like to put parentheses whenever I'm working with binomials, anything more than one term. And then I got rid of those parentheses. I just made some rearrangement here. I wrote x squared up front, and then guys here, the other thing I did was I got rid of this function notation thing, so that it's not confusing for us, okay? So now let us focus on this equation. From this equation, keep in mind our goal is what? Our goal is to find dy over dx. And that is not too difficult because we already know how to solve algebraic equations. So from here, guys, from here, we can clearly see that this term and this have dy over dx is the common factor, or basically it's also the greatest common factor. So what we can do here is, first of all, you know what I'm going to do? Since I want to solve for dy over dx, my goal is to isolate dy over dx to get dy over dx by itself. I don't like this term on the left hand side. First, I'm going to bring that term to the right hand side. So I will subtract 2xy from both sides. If I do that, this is what I'm going to be left with. I'm going to be left with x squared dy over dx. I'm just rewriting this, and minus 2y dy over dx. And when I bring this to the other side, it is going to become negative 2xy, okay? Negative 2xy. Guys, now I want dy over dx by itself, and I can clearly see that dy over dx is the common factor or the greatest common factor between these two terms. And what do we usually do with the greatest common factors? We just take them outside, right? Dy over dx, and then what is left inside the parentheses? From this we have x squared, because x squared times this is going to give us that back. And then from here we have a 2y. Right? Guys, when I distribute this, I should get back that previous step. And this is equal to negative 2xy. So we're almost done, guys, to get dy over dx by itself. So let me actually get rid of this so that I have space here. So guys, to get dy over dx by itself, all I have to do is I have to divide by this quantity, because that quantity will cross out and I will be left with dy over dx. So I'm dividing both sides by, of course, if I divide the left hand side, I have to divide the right hand side as well. So I divided both sides, this crossed out, I get dy over dx, and that is exactly what we were trying to find. It says find dy over dx equals to negative 2xy over x squared minus 2y. And guys, this is going to be my final answer. Now, if you are little surprised to see that, because so far we have always tried, we always found the derivative for explicit functions. So the derivative was also always either a constant or it was in terms of x. Guys, what is different here is that you have some x terms, but you also have y terms and some constants as well. But guys, that is totally fine for implicit differentiation, because we may not be able to clearly solve for y right away. So if we get the final answer with y terms, that is totally fine. Okay. So again, there's some steps. This is something slightly different than what we have done so far. But guys, if you ask me, I don't think it is like anything different. It is just like using the chain rule. But there's only one key thing that one has to keep in mind. You see that you kind of treat that as y, or a function of x. And that is what I did by actually writing it as y of x. But now, guys, now onwards, once we understand this first example, I'm not always going to write y as a function of x. We already know it's a function of x. When we take the derivative of y, we already keep in mind that it's a function of x. We have to multiply by the derivative of that inner.